time we were talking about this, which this graph shows for a case that we had made several assumptions for, which are listed earlier on the notes, shows the ratio of the receiving to the sending end line voltage magnitude versus the x-axis, which is the received power over the surge impedance loading, which, remember, the SIL is sort of like the nominal value that we have for the load. So this right here, 1.0, is sort of like it being loaded normally. The further you go to the right, the more heavily you're loading the system. And what we did was, I mean, you could draw an infinite number of these curves right here, the green, blue, purple, because we were picking different power factors. But if we draw this relationship, right, we have 0.9 lagging power factor, unity power factor, and then 0.9 leading power factor. And so the main takeaway from this is that this curve shows you exactly where the system becomes unstable, okay? And it's at the tip of this, what we call a nose curve. Now, the thing is that, right, we can draw this curve for a very simple system where we have the assumptions that we had. But for a very complex system, like we'll see later on, unfortunately, you can't draw these curves exactly, or not without doing tons and tons of work, and your nose curve would only apply to a single case, so it wouldn't be particularly useful. So later on in this class, and a lot of times in power systems in general, you'll hear engineers talk about the tip of the nose curve and instability, but it's not like we'll actually physically know where that is. However, there's a lot of things we can take away, right? One is, again, seeing the increased rate of change in the voltage magnitude downward as our loading increases. But, I mean, that's kind of something you expect to see with any instability, right? As you push it further and further, once things start to run away, you would expect that you're getting close to instability. For some of the power system analyses that we'll do, you'll see that we'll come up with two different solutions. One will be the top of the curve, one will be the bottom of the curve, and you'll just know that the bottom of the curve is the unstable solution. So you can always negate that. So it's a pretty useful graph, more so in terms of describing the characteristics of a power system. But very soon, I think by the end of this class, we're going to get into load flow, which is the actual way that we solve for the state of a larger system, which is more complex mathematically and has less to do, and moves almost more to like a math class sort of material, and less focused on the power end of things. Okay, so before we move on to load flow, there's just one thing that we have to tie up here, and that's going to be section 10.4, which is prevention of voltage instability. So it's nice to know when instability is going to occur, but if you can't do anything about it, right, it's really not too helpful in general. So we saw that, heavy loading leads to the instability. That's not anything groundbreaking or rocket science. Again, something that you see in a lot of a lot of engineering-based systems. If you're looking at like a bridge or something like that, the closer you get to the instability point, usually that'll result from higher loading. Now the lessons that we learn and this is what I was talking about before. The lessons that we learn from this radial system, they do apply to larger systems, but in sort of more of a qualitative manner, describing the general behavior of the system. Not so much, again, we're not going to be able to draw the nose curve for every single bus in the system, at least not in any practical way. And we also see that the instability is associated with a shortage of reactive power. If you remember, going back to previous parts here, we talked a lot about the need, like right here, for the Q being supplied by either end of the line to, I mean, in this case where it was unity power factor, the Q line needs to be half supplied by one end and half supplied by the other end. And so if we can't meet those, if the system can't meet those requirements, that's one of the main things that will lead to the instability. And so, yeah. Okay, so section 2.4.1 10.4.1, I said 2.4.1, is focuses on synchronous generators. I mean, we spent a lot of time talking about synchronous generators, right? All that chapter 9 stuff was all on synchronous generators. So this is not reteaching that. This is talking about the role that it plays specifically in instability. Okay, so right, the amount of Q that a generator can produce is not, is not infinite, right? It's it is limited, and so this figure that I'm going to draw in 1 second, 10.5, illustrates how a generator reaches its limits. Because right, stability is associated with the Q being supplied on the receiving and the sending end. The sending end is going to be a generator. And so what happens here? And the reason why this all falls under the section titled Prevention of Instability is because right? One of the main ways that we can prevent the instability is by using the excitation control system of the generator, right? We know that there's two main ways that we've been able to manipulate Q. One is using shunt capacitances, which we call power factor correction, and the other is the excitation of the generator field lines. Okay, so the x-axis for this graph is going to be P generated. The y-axis is going to be Q generated. And so this is going to be supplying. This is going to be consuming, just to get our bearings. And this right here is going to be our Q max value. This right here is going to be 2, 4, 6, 7, 2, 4, 6, 7. This is going to be our Q min. And we're going to split this up into several different regions. I'm going to try to draw this sort of to scale. Needs to be a little bit lower. So what is that? 2, 4, 6. Okay, so sort of like this. And then now, to actually draw the PQ relationship itself. So I think this will work. Okay. All right. So, right, you can supply, the reason why there's a top and a bottom end of this curve, right, is you can supply a certain amount of real power and be consuming Q or supplying Q, so you can be on the top or the bottom here. Now we're going to name these, we're going to call these regions. So this will be region B. This will also be part of region B. The whole thing that's between the blue and the green. And then region A is here, and that'll be everything that's between the two green lines. Okay. So, some notes. As you would expect, it's easiest to produce more Q when you are not producing a lot of Q, right? When you're down here, for example, increasing the Q value, and you can see this by the curve, right? How the curve becomes flat at the top. When you're not producing much Q, it's easy in terms of there's not that much of a change in excitation that needs to be implemented to increase Q. As you get closer and closer to the maximum, it starts to level off and it becomes very hard, and then eventually you reach your Q max value. This intersection, same point here. Indicates the rating in MVA and power factor for the rated voltage magnitude. This intersection indicates MV Okay, so and we'll talk about what region A and B mean. Sorry, this is actually called region C. You could call it B also, but anyway, we'll keep it separate. So the differentiation between A and B or A and C is a line that goes from the origin to this point, which is set by the rating in MVA and power factor. So the rating could be right here, could be 10 MVA, and then the power factor angle, right, would be whatever it's rated at, 30 degrees or so, and then you would, the two of those together would give you the intersection. Okay. So, now the interesting question, or the more interesting question here, is what do these regions mean? Specifically as far as the generator's operation. Okay, so region A. The reactive power is limited by the heating or the power loss, however you want to say it, through or of the armature coils, windings. And this makes sense because we know more Q means higher magnitude of the current going out. In region B, the reactive power is limited by the heating of the field windings. And these are two very different constraints, right? Because the heating of the field windings is actually a constraint on the excitation system itself. Okay, and when you're in region A, you can keep turning up the excitation system. It won't have any ill effects on the excitation, but you'll be overheating the generator itself. When you get into part B, up here, right, now what you're seeing is that you're actually overloading the excitation system. So the difference between A and B is really how the reactive power is limited. Limited by the generator or limited by the excitation system. And so here we can say that's the other reason why in region B the armature winding is not the problem, is because also now, right, we know that the current will be a function of P plus JQ. So if P goes down significantly, then that's going to alleviate, regardless of how high the Q value gets, that's going to alleviate the armature winding problem. So when you go from A to B, your P is coming down, your Q is going up, the problem of the armature winding goes away, the problem of the field winding heating emerges. Let me look at one thing. Okay, so region C, there was a reason why I labeled them both B. Region C is similar to region B. Hold on. Yeah. So C is similar to B. All right, so as opposed, this is the last part of this text right here, and it's a lot to write, so I'm just going to read it, and then we're going to move on to load flow, which actually has a separate set of notes that we'll be using. So traditional excitation control systems are often too slow to prevent stability or to prevent instability. So what does that mean? Right? Even though we're talking about how lack of Q is very closely tied to instability. In an ideal world, the generator should be able to account for that, but they're too slow. So it doesn't provide a solution. It provides a solution for instability that may be caused by slow-moving factors. So what's an example of a slow-moving factor that can cause instability? Is just too much load and, let's say, a dip in renewability. Okay, let's say you have an area that's reliant on solar, and you have a continuous over hours, 5 or 6, 7, 10% decrease in output as compared to what they would expect. And it's a little bit colder than one might think, and so people start, or say hotter because the AC uses more power, so more people are turning on their air conditioning. So that would be the example of like a creeping towards, slow movement towards instability. And in that case, you could use the generator excitation control system to overcome that. It would not be very helpful in the case of like lightning striking a line or some sort of very sudden outage or something like that. So what alternative options exist to improve reaction speed? One is called the fast-acting thyristor. A thyristor is a kind of a solid-state switch. And so we'll talk about this a little bit later on, but there's various power electronic devices that you can build that use shunt capacitors in order to supply reactive power very quickly. So fast-acting thyristor-based hardware in conjunction with a power system stabilizer to dampen oscillations. Without giving too much detail on that, it's a switch hooked up to a capacitor that has a closed loop feedback, and so it can read the need for increased Q. That's often going to be indicated by the voltage magnitude dropping, and it can switch in and out those reactive power sources automatically. The second alternative is to constantly operate the generator in a state of overexcitation as a reactive power reserve. So you could always just say, well, I'll just always run the generator, giving us more Q than we need, which, if we go back to this graph here, right, we see that by pushing our power factor towards leading, we're always going to be moving the tip of the nose curve outward. So that would be an example of running the system in a very conservative manner. But the downside there is you will need a reactive load to consume it most of the time. Any imbalance is going to be problematic and can actually push us to instability in the other direction. One of the assumptions about this graph here, if you remember, is that the Q at the receiving end is equal to the Q at the sending end. So all the Q that we're generating is somehow being consumed. So you can use overexcitation in order to improve the stability of the system, but you have to have some way of consuming that down the line. Okay, so that brings us to the end of what we're going to be doing in Chapter 10. Okay, and so I would like to assign some homework, which I'm just going to write at the end of the notes here. A lot of these homework problems call back to Chapter 5, which is actually the next thing that we're going to discuss. But it's going to be hard to assign these right now. Right now, I'm going to leave the homework just as 10.5. This afternoon, what I'll do is I'll go and take a look and see if I can find a homework problem, some homework problems from previous implementations of the course that I can throw in there that won't be from the textbook, but they'll be relevant to this Chapter 10 material. Okay, so what's next? So next, we're going to switch gears a little bit, and we're going to talk about load flow analysis. And for this, we're going to be using an older set of the notes. I didn't bother remaking the notes to fit the notation of this textbook. It's very, very similar. And so I don't see it being problematic. But if you download the lecture notes, the 2010 to 2015, those are the ones that we'll be using. But just one specific part of it. So these notes are actually a good additional resource if you are interested in other stuff related to power systems. It touches on some of the same topics. Obviously, Chapter 1 we dealt with. It was Chapter 2 in this new textbook. Chapter 3 is the synchronous machine, which is sort of like what we talked about in Chapters 4 and then 9 a little bit. Transmission line, we talked about that a little bit also in Chapter 9. And then this is what we're going to be talking about now, which is load flow analysis. Okay. I'll fix these question marks tonight. Every few years, the fonts for the symbols, there was an old tool I used to use called MathType before Word had the symbol editor in it, and so every few years the fonts go away, so I have to replace them and they'll come back, but I'll fix it. So, what is the power flow problem? We essentially want to find the state of a power system. Yes?
What chapter does this correlate to?
This correlates in this book to chapter 5. Yeah. Same name. Power flow in power systems, and then in the old textbook, power flow analysis. Okay. So the power flow problem, we want to find the state of an N-bus transmission network. So far, we've been dealing with really small systems, right? These one generator, one load, generator connected to infinite bus. It was a great way to look at instability and look at certain ways in which the generator operates, the synchronous machine operates, but doesn't allow us to solve bigger problems. So now we want to find the state of a system that has multiple lines, has multiple transformers, multiple generators and loads all working together and interacting. And so now here is the model that we're going to be using for a power system. The most basic example is going to be what we call the 3-bus system. So the 3-bus system has an infinite bus. Okay, we already talked about what the infinite bus is, right? The infinite bus can supply an infinite amount of P and Q. It's defined by its voltage magnitude and its voltage angle. So it will always have, most of these problems will be working in per unit, so it will always be 1 with an angle of 0. All right? Then our generator bus, which we're not going to be using the model that we have that we derived in chapter 9. We're going to be using a simpler model. And we're going to be using simpler models for pretty much all the components because of the system size getting larger. For a generator bus, we're going to, another word for that, we're going to call it a PV bus. Okay? So a generator bus is going to be defined by the real power that it's supplying to the system, as well as the magnitude of the voltage at that bus. So for a generator bus, you may know the magnitude is 1.1 per unit, and you know that it's outputting 0.5 per unit real power. You don't know what the angle is, and you don't know what the Q value is for it. So when you're solving the power flow problem or the load flow problem, those are the two values that you're trying to get. You're trying to get the delta, and you're trying to get the Q. The third type of bus is the load bus or the PQ bus. And so for that one, you don't know any of the voltage magnitude, any of the voltage values, magnitude nor angle. You do know the P and the Q either being consumed or injected. It's irrelevant. Okay, we can just define them as negative or positive values. So for each one of the buses, there's 4 values that we're concerned with, and we'll know 2 of the 4. Either we'll know voltage magnitude angle, voltage magnitude and P, or P and Q. And then the voltage, the load flow problem, is tasked with solving for the others. The lines, if you remember, when we talked about transmission lines briefly, we talked about something called the pi model. We're going to, in most cases, be using a pi model. So you'll have a series element and 2 shunt elements on either side. And that will be purely, that'll be a constant impedance. Okay, so now we can solve for more complex systems, but it's really just going to be repetition of these bus types. More PV buses, more PQ buses added on. We get to larger and larger systems. Normally, we won't have more than one infinite bus in a system. And why do we need an infinite bus, period? Okay. Why don't we just have 2 PV buses and a PQ bus? The reason why we need an infinite bus is because the problem becomes over-constrained without the infinite bus there, which means that if there is a solution that exists, it will be very hard to find it mathematically. And in most cases, there won't be a viable solution. The reason being, the loss within the transmission lines is highly variable. So in order to find a viable solution, all the P's and the Q's must add up to 0, right? The P generated minus the P consumed minus the P lost along the lines has to be equal to 0 in order for that to be a viable solution. Same with Q. And so you can see that unless you set the generator and the load values up to very specific values, there's not going to be anything that's going to satisfy that. And so the objective, find the state. Find the voltage, magnitude, and angle at all the buses, which in turn is going to give us the P and the Q at all the buses as well. All right. So this idea of load flow analysis is really tied to nonlinear system analysis. If you go back to ENG 212, we have various ways of dealing with electric circuits. Nodal analysis, mesh analysis, all that type of stuff. Why can't we apply that here? Okay? Actually, does anybody know? Why can't I apply nodal or mesh analysis to the 3-bus system that I have above? Because nodal and mesh analysis only applies to linear systems. The power system up above, the way we describe it, is nonlinear, and the reason why it's nonlinear is because we're not describing the loads and the generator as resistances and sources. So if all the loads in the system, instead of being PQ, if we describe them as RX, and if we described all the generators instead of PV, we just made them voltage sources, then you could go ahead and apply nodal and mesh analysis to it. But that's not the accurate or the best way of describing the way that the system works, and so we are left with a better description that's going to be harder to solve. So the best illustration of that is this really simple example right here. So this is a DC network, a really simple example, but you'll see why we can't just use KVL, KCL, nodal mesh analysis in order to solve, and we'll also get a really simple look at how we actually are going to solve it. The method is sort of similar to, it's iterative in nature. If any of you remember from electronics, we talked about the iterative methods for solving for the voltage across a diode. It's sort of going to be rooted in those types of methods. Okay, so let's take a look at what we have here. 2-bus system, voltage source with a value of 1 volt. Resistance along this line, 0.25 ohms, and bus number 2 is defined by its P value. So there's 1.2 watts that's flowing into the system. So how would we solve this? All right. For this one, we can just set up some basic equations in order to solve. It's a really, really simple version of what we're going to be looking at later on. So this is one I think that's really intuitive. Okay, first things first. The current along this line here, I21, is going to be equal to E2 minus E1 over the resistance 0.25 ohms, right? So that's what's shown right here. We don't know what E2 is. However, we do know what P2 is. So let's go ahead and take this value of I21 and let's multiply that by V2 and get what the value of the power, real power coming into that bus should be. So P2 equals V2 times I21. We substitute this value, we pull it in here, and we end up with 4 E2 squared minus E2 equals 1.2. So this equation equals 1.2, which is the same 1.2 that we're pulling from up above. You guys see what we did here? We calculated this expression. Then we know that P equals VI. We take that and plug it in for I. And V2 and E2 are just used interchangeably. It's the same value. And then lastly, right, we'll solve for E2. So if I move some things around, you'll see this ends up being a quadratic equation, right? 4x squared minus 4x equals negative 1, 4x squared minus 4x minus 1.2 equals 0, right? If I substitute E2 with x, that's our unknown variable, it looks like a quadratic equation, the kind that you're used to seeing. Here, it's written like that here. Except that's a typo, that should be minus. You can see I used minus below for the C value, that should be a minus. And so we can use the quadratic formula in order to solve, and we'll end up with two different solutions. We'll end up with a solution of 1.24 volts, and we'll end up with a solution of negative 0.24 volts. Just from, right, this is b plus or minus the square root of b squared minus 4ac times, or divided by 2a, the same old quadratic equation that you've used a million times before. So we have two different choices for the voltage at bus number 2.
Is one of those voltages more correct than the other?
Most definitely. We're going to talk about that in 1 second. Yeah, only one of them is correct, which I guess I don't discuss. Well, for a DC system, we don't have a problem of stability, so I guess either one of these could apply. Yeah, for this case, for this very simple case, either one can apply. When we move on to more complex problems, you'll actually use the whole idea of the nose curve in order to determine which is correct and which is incorrect. So for an AC power system, if you end up with two values, the higher one will be the top side of the nose curve, and the lower one will be the bottom side of the nose curve. We already know that the bottom one is unstable, so we'll automatically pick the top one. Okay, so what are we trying to show in this example here is just a very, very simple way of solving a nonlinear system. A quadratic system, or a system that's represented by a second-order polynomial, is nonlinear. It may not be the most difficult nonlinear expression to solve, but it is nonlinear in nature. Okay, so now let's take the difficulty of this and let's step it up just a little bit and add a third bus. So now we have this case here. So we have, it's essentially the exact same system. P1 is the same, E1 is the same, R12 is the same, P2 is the same, but this chunk in here, this is new. We've added a third bus, and then the lines that connect those together. And so now what we need to do is to calculate all of the different currents. So, and the reason why we calculate the currents is because that will allow us to calculate the powers, right? To put them in terms of the value that we know. Again, P equals VI. The V is going to be a variable that we're going to try to solve for, but we need to calculate a representation for I. So what is I1 going to be? This actually, I'm going to skip because I1 is not going to be so important since we already know what E1 is. I'm going to start off with the second row. Okay, I2. So in this class, when they use a single subscript, okay, as opposed to two subscripts, we know what I23 is. I23 is the current flowing between bus 2 and bus 3. We know what I21 is. It's the current flowing between bus 2 and bus 1. I2 is the sum of all the current flowing like this into the bus. So it makes sense. I2 is going to be equal to the sum of I23 plus I21. I23, this is just going to be using KVL, V2 minus V3 over R23 plus V2 minus V1 over R21. Anyway, I digress. If you write out all of these equations right here, this is essentially the same thing as setting it up for nodal analysis, right? You end up with 1 over R1 plus, you have the let me show the matrix form. If you take these equations and put them into the matrix form, you end up with this, right? This is the form that we're used to seeing when we set up our admittance matrix for nodal analysis. I related to V, and then we have this 3 by 3 matrix. The problem, which I've already hinted at before, is that, right, we don't know these currents and we don't know these voltages. So we can't use one to solve for the other or a combination of them to solve for one another. All the problems that we saw in ENG212, we would either know these values or some combination of the V's and I's. This is unknown, these are known, and this is unknown. So this form of the problem doesn't really help us that much. The other thing is that this problem also we can't solve using the quadratic equation. Okay? The quadratic equation only helps us for the first type of problem because it's very small and there's only one variable that we're looking for. If we try to set up something similar to the quadratic equation for this one, let's say, for example, we try to calculate P2 in terms of V2, what we'll end up with is a mixture of V2s and V3s. Okay? And so we can't use the quadratic equation to solve for this guy. P2 equals alpha V2 squared plus beta V2 plus, and then you have a term that includes both of them together. In the first example, we only had V2s, and so we could solve. Now we have V2s and V3s, so that completely screws that up. Now, so how do we solve this? One way is to start from an initial guess and do this iteratively. So hold on one second. Okay, so let's get into the nuts and bolts of how this is going to work, step by step. So what we're doing is we're going to be looking at the first power flow example. And this is for the DC system. I'm going to quickly draw the system just so we can use it as a reference. We have a DC source here. It's connected to some sort of a bus. We have a resistance. It's going to a third bus. Okay, here we have a value which I'm going to call negative P3 because I have it pointing downward and they have it pointing upward. And then this right here is negative P2. This is voltage V1, this is voltage V2, this is voltage V3, this is R12, this is R23, and this is R13. Okay, so that's everything that is told to us. And then the values, I'll quickly write them down. R12 is equal to 0.25 ohms. R13 is equal to 0.1 ohms. And R23 is equal to 0.2 ohms. P1 is equal to 1 volt. P2 is equal to 1.2 watts. And P3 is equal to negative 1.5 watts. So you see that a lot of this mirrors the 3-bus system that we talked about in the very beginning, even though it's DC. Okay, this is an infinite bus, right? It can supply an infinite amount of real, and there's no reactive power in this case, but infinite amount of real power. And so the voltage there is known. This is what we can call a load bus or a PQ bus. But again, in this case, there is no Q, so we don't, that doesn't come into play. All right, so, and we know for this, so we know that nodal and mesh analysis won't work because it's nonlinear. We also know that the quadratic equation won't help us anymore because it's nonlinear but beyond having a single variable to solve for. So now we're in the more complex case. Okay, so how can we solve this? So let's try an iterative method. And let's start with an initial guess. So what I'm going to do is I'm going to say we're going to have V1 old, and that's going to be 1.0 volts. We don't really have to make an initial guess for V1 because we know what V1 is, right? I'm going to say V2 old will also be equal to 1.0 volts. And then I'm going to say V3 old is going to be equal also to 1.0 volts. So I'm just going to guess that all three of them are 1.0 volts. What does old mean? It essentially means it's the first value that we have, and we'll call the next one new. Later on, we'll start using iteration numbers. We'll call them the 0th iteration, first iteration, etc., etc. Okay, so now we can try to solve the system algebraically as if it were linear, okay? The thing that was preventing us from doing that was the fact that we didn't know, we couldn't represent the buses, right, as voltage sources. Now, with this initial guess, we can. And so we can treat this, along with that assumption, right, like it's linear in nature. So let's Okay, so let's solve for V2 new. How do we do that? We know that I2 will be equal to P2 over V2. That's just basic, good old circuit analysis. Before, we couldn't use this expression because we didn't know what V2 was. But now we can go ahead and substitute in, and we'll say this is V2 old. Okay? We also know that this will be equal to I21 plus I23. And that in turn is V2 minus V1 over R12 plus V2 minus V3 over R13. And again, we don't know what V3 is, so I'm going to go ahead and say V3 old. And these guys, I'm going to call V2 new. So what we're doing is, so we're going to call at least one value of V2 old. We're going to call at least one value of V2 new. To tell you the truth, you can do it lots of different ways. We could switch it around. I could call the one in the denominator new and call the other ones old. I could use some different combination. It's not that it doesn't matter. It can be easier or harder to solve in some different ways. But we'll be able to solve it regardless. Now, what is going to be the goal here? We're going to want to come up with a value of V2 new, which is based on V2 old. Right? That'll be the basis of our iterative process. Yes?
How will we know like when to stop the iterative process?
So like a lot of iterative processes, when you start getting the same answer over and over again, you'll know to stop. Okay. There's also other constraints that we can look at when the calculated and the known values match one another. So we're going to calculate a new value. The value we get for P2 is not going to be the same as 1.2 watts initially because our solution won't be exact. When we start calculating P2 as 1.2 watts, and then it equals the value we know, and that applies for all the different buses. That's also another condition we can use for convergence. Yeah.
Are we plugging P2 in? So when we list it, P2 equals 1.2?
Yes, you are, but you can also calculate P2 using this expression here. P2 equals so you see what I'm saying? You can update it each time. We're assuming the P2 is equal to the known value when we do our update, but when you actually use the new value of V2 and the new value of I2, that won't match exactly. So you'll get a new value. Okay. So let's switch some things around here. So what we will have is, okay, so P2 over V2 old is equal to V2 new times 1 over R12 plus 1 over R13 minus V3 old 1 over R13 minus V1, which is known, 1 over R12. And switching it around some more, so I'm going to take this, I'm going to move this over here, I'm going to move this over here, and so what we'll be left with is V2 new equals 1 over R12 plus 1 over R13 times P2 over V2 old plus V3 old, 1 over R13 plus V1, 1 over R12. Now, I'm going to start using a little superscript here in order to separate the calculated and the known values from one another. I'll start calling that the injection, okay, which is just another way of saying that that's the known value. And so we know all these. Now this will be 1.2 watts. This will be 1. This will be 1. This is 1. And the other resistances are also known, right? So we're taking a whole bunch of either known or assumed to be known values, and we're plugging those in, and we end up with a value of 1.13. Now, but we also have to do the same thing for V3. And so we're going to set it up in exactly the same way. We're going to say I3 is equal to P3 injection over V3 old is equal to V3 minus V2 over R1 over R23 plus V3 minus V1 over R13. This is going to be the new value. This is going to be, so here, which do we use? There's actually two different methods we're going to learn. One's called Gauss, one's called Gauss-Seidel. One uses the old, one uses the new. There's really not too much advantage to using the old because your assumption is that the newer value will at least be closer to the accurate than the older. There can be some cases where that can lead to a problem with the convergence, but we'll just go ahead and move forward with the assumption that anytime we know a newer value, we're going to go ahead and use the newer value. Okay. And so the form of the equation ends up being exactly the same as this right here. And so what we'll end up with is, after we switch some things around, the same algebra, V3 new is equal to 1 over R13 plus R23 times P3 injection over V3 old plus V2 new 1 over R23 plus V1, which is known, 1 over R13. If you want to go back and do that algebra on your own, you can, but it's a repeat of what we've shown above. And again, all these values should be known. We know these guys, the resistances are clearly defined. This is equal to 1.0. This will be equal to 1.13, right? Because we got that above. This will still be equal to 1.0. This is equal to negative 1.5 watts. And so when we go ahead and plug all that in, we end up with a new value of 0.9433. And so we continue with this process. And so you can do it in Excel or whatever. And you end up with something that looks like this. So you can see that for the first iteration, so the red is V2. So for the first iteration, it jumps up to 1.13. And then in the second iteration, which we're not going to do by hand, it actually comes back down and settles on a value, I guess, closer to like 1.08, 1.09. Yeah.
So when we go back to the second iteration of it,
Mm-hmm.
instead of using V2 old, do we use our V2 that we calculated?
Yeah, so this is going to be a lot easier when we start using iteration numbers instead of old and new. The way you could think about it is you would, when you set these equations up the next time, you would have to call it V2 newer, and then you would use V2 new as the inputs. I mean, and again, after this example, we're going to stop using old and new. We're going to call it 0th iteration of V2, first iteration of V2, and then when you use the numbers, it makes it a lot easier to keep track of everything. But for the first example, I think using old and new gets across the idea a little bit better of how they relate to one another. Okay, so that's really the first load flow example. And it gets across a solid 80 or 85% of the concepts that we're going to talk about in this chapter. The part that we haven't talked about so far is how do we deal with, AC values and the difficulty that we don't really have an example of a PV bus in here. But if you understand this, and I would take a look at this offline again, if you can understand this one and get a good handle on what's going on, it's a very good start for this chapter. And really look at what we're doing up here is we're just comparing two different definitions for I2, right? We know that I2 is equal to P2 over V2. We know that I2 is also the sum of the individual currents. So this is essentially a constraint, right? The constraint is I2 must equal I2. Obviously, for anything has to equal to itself. You could also set up a version of this iterative analysis where it was based on P2, saying P2 equals P2 or V2 equals V2. the equations would be a little bit different, but you would still end up with an old version, a new version. For this type of system, using the current makes the most sense because it requires you to do the fewest number of substitutions, and it essentially presents all the values there that you need, which is V old, V2 old, V2 new, and the other voltages as well. So all we're doing is setting the current equal to itself, but in one case we're using the old voltages, in the other case we're using the new voltages, or you could say in one case we're using the 0th iteration of the voltages, in the next case we're using the first or the newer iteration of the voltages. And like it's shown on the computer screen, you can just run that over and over again until you reach convergence. But before we move on, let's address the point. Yes.
The V1 that's still the old value, right?
Well, so V1 is known. V1 is if you look at the system, the way it's defined, it's 1. So, and that's similar to the role that the infinite bus is going to play. So we don't have to do any work for the infinite bus.
So in the beginning, we defined that as 1 volt, or we defined V2 old and V3 old as 1 volt because V1 was 1 volt.
So the initialization is almost a completely different subject than the analysis itself. There's like people who write entire papers on just how to initialize these type of things. For 99% of the cases, we're going to use what's called a flat start, which is 1 per unit, 1 per unit, well, essentially 1 per unit for all the buses. This is a little bit different because this is not a per unit problem. This is in volts and it's DC. But we can assume here that because E1 is 1 volt, that's sort of like the rated value for the system. So yeah, in most cases, we're just going to use 1 across the board, 1 per unit across the board. If you have any clues about a better starting point, then you should use them. Let's say, for example, you previously solved a load flow problem that was the exact same system, but now only a couple of the values have changed. Like let's say just a couple of the power values have tweaked a little bit by 5 or 10%. Then what I would say is, as opposed to using a flat start, you should use the solution you got from the previous load flow as the initial condition for your new one. But for most of the problems that we're working with, you're not going to have any information like that, so you're just going to be stuck using a flat start. All right. So now AC networks. So how is dealing with the AC network going to be different? It's only going to be different in terms of the specifics of the algebra, but not much else. It obviously is going to make the math like twice as tedious because now you're solving for 2 values for every bus as opposed to 1, and so there's that element of it. We've already gone over these equations. We know that the voltage at bus I can be denoted in a polar form. It'll have a magnitude and an angle. We know that we'll have our lines defined as their complex impedance or complex admittance. Right? Which is R plus JX or G plus JB. You can also represent the admittance and impedances in a polar form where they'd have a magnitude and an angle. Any of the complex values we can represent in a polar form. The current can be depicted in as a sum of so the current injected into a bus can be defined as the sum of all the currents flowing out of that bus. So this equation right here is essentially the same as this right here, the right-hand side. I2 is equal to I21 plus I23. And so we have the sum of the voltages and the admittances, right? Because 1 over R12 is the same as the admittance between buses 1 and 2. 1 over R13 is the same as the admittance between buses 1 and 3. And so the form that they show it, they're not talking about, so there's a difference. YIK represents the admittance between two different buses. YIK with this superscript bus, what that's saying is that's going to be the IK element of the admittance matrix, which you know as the matrix we use for nodal analysis. Okay? So Y11 would be this element right here, Y12 would be this element right here, Y13 would be this element right here. And you know how to make that, that matrix from doing nodal analysis. And we'll do examples, lots of examples on this, and spend lots of time going through the mathematics of it. So this is going to be sort of the opposite of maybe the last chapter and a half, where it's been a lot of information with a very limited payoff in terms of the application, fewer examples. This is going to be less information relatively, and just a lot of examples and repetition on how to apply it. But hopefully you're familiar with what an admittance matrix is. Complex power, S equals VI conjugate. We can take this definition of I and plug it in here, and that'll give us V, and then this form, which is the sum of the Y buses and the voltages. And that's also equal to the real plus the reactive power. Okay, so those are all equations that you should have seen in some form before. But the reason why we've highlighted them here is because they're really important for doing the work in this chapter. Okay. So now, these equations, which are called the power flow equations, hence the name of the chapter. So what these equations do is they define the injected or the calculated value of power flowing into bus I, and the calculated value of the real power flowing into bus I and reactive power flowing into bus I. They look a little bit complicated, but when you break them down, you'll see that you know all the individual pieces. First thing, sum from K to N. All this is saying is that you have to consider all the different lines going out of the bus. From K equals 1 to K equals N, where N is the number of lines going out. So let's say there's 3. You have to consider line 1, 2, 1, 3, and 1, 4. All right? The bus that we're talking about is called I. So this is the voltage at the bus in question. This is the voltage at the other bus. Right? Remember, we're essentially considering each line individually. So if the first term of this sum is going to be 1, 2, it would be voltage 1 times voltage 2. The 1, 2 element of the Y bus matrix, which would be this right here, this element, 1, 2. Times the cosine of the voltage angle at bus 1 minus the voltage angle at bus 2 minus the angular component of whatever Y bus 1, 2 is. right? This is the magnitude of whatever that element was, and this will be the angle of it. So the inverse tangent of x over r. Q is the exact same thing, except we're going to be using sine instead of cosine. Yes?
So Y bus is just an impedance like matrix?
It's the admittance matrix.
Admittance?
Yeah, which is 1 over the
Yeah,
impedance matrix, or the inverse of the impedance matrix. So we're going to be using these equations a lot. I'm going to try to cut back on the derivation a little bit in this chapter. But this equation right here, or these two equations that constitute 203, they are just a compilation and a combination of equation 199, 200, 201, and 202. All of these equations that we've seen before, combining them together gives us this version. Okay? And so, applying these, let's say what we're going to have to generate, if we have 3 buses in a system, we're going to have to use 2 different sets of these equations. The reason why we only need 2 is because we don't have to solve for the infinite bus. So we're always going to be solving for 1 less bus than we have. So if bus number 1 is the infinite bus, then we'll be setting up these equations P2, Q2, P3, Q3. We don't have to worry about P1, Q1. Okay? And so these equations we're going to use in a manner very similar to what we did here. We're going to define certain voltages inside of the power flow equation as old or previous iteration. We're going to define certain variables of voltages in there as new or next iteration. And then we're going to shift it around algebraically to find a form so that we can do this iteratively and keep updating the voltage values. Again, the difference between YIK and YIK bus, we've talked about this several times, but this actually explains it. So the Y bus matrix or the admittance matrix is composed of the individual YIK values. So for example, right, Y bus 11 is equal to Y12 plus Y13. So if you don't see that bus, and you'll see it both ways. Usually it's lowercase versus uppercase also. But look out for that superscript. If you don't see the bus superscript, then you're simply using the actual admittance along the line. If you do see the bus superscript, then you're using the element of the admittance matrix that corresponds to it. Okay. Now, in the power flow problem, there's several different types of power that we're going to be dealing with, and we've already used them. So here, in the example, the powers that were given here, we're going to call them the power injections. We can also call it the scheduled power, meaning that that's the value that we expect to get once we have solved. The other kind, if you look back here, is the calculated flow or the calculated power. And so that is going to be the value that you get when you multiply V2 new times I2 new. Okay? Those two values, this and this, will match once you've gotten to a solution. But before that point, they should not match. The difference between them is what we're going to call the flow mismatch. That's the difference, right? The difference between the calculated and the expected, or the calculated and the scheduled flow. And so here you see a little example for one bus, which is I. Okay, the power injection is going to be, or the scheduled power flow will be the difference of the generation minus the demand, because at buses you could have both, all right? A lot of times we're going to be aggregating lots of stuff together when we define the way that a bus works. So you could even be told for bus number 2, you have a P generation of 2 megawatts and you have a demand of 0.5 megawatts. Okay? What is the scheduled flow? It'll be 2 minus 0.5, and the net difference will be 1.5. So that'll be the scheduled value that you'll use. And that should be equal to the calculated flow along all the different lines summed together. All right, so the mismatches. The mismatch in P for bus I will be equal to the calculated value minus the injection. You can also break the injection down to the generated minus the demand, like the example that I just gave. Same thing for Q. Delta Q will be equal to the calculated QI minus the generation minus the demand. So if you, no, there's not really an example of that in what we did. Okay, so what is the significance of delta P and delta Q? The goal of the power flow problem or the load flow problem is to find a solution or a system state which brings the mismatch down to 0. Delta P equals 0, delta Q equals 0 for all the different buses. And what that represents, so you can think of the set of power flow constraints as defining a surface in an n-dimensional space. This is sort of like the mathematical way of defining this. And when we reduce the mismatches to 0, we're finding a solution that falls on the surface there. All the potential solutions to the problem, the surface here represents all the potential solutions to the problem. Okay? That will correspond with different inputs. Anything that doesn't lie on the surface, or when the mismatches are not equal to 0, is not a viable, physically viable solution. What that means is it's going to violate some law of physics. Most commonly is going to be conservation of energy, conservation of power, right? The power or energy or current going into a bus doesn't equal what's coming out of it, or going into a line doesn't equal what's going out of it. Yes?
This is maybe a stupid question, but is like the delta P and delta Q in this case kind of like is this more like a gradient on the surface?
Well, it's different because delta P and delta Q don't refer to the tangent to the surface right there. What they do is represent the distance between where you are and the closest point that lies on the surface. So, you know, this is the surface right here, we're up here. The distance between the two would be determined by delta P and delta Q. Okay, a little bit of repetition here. We have 3 different types of buses. The naming conventions, the names that are used can vary a little bit. You'll hear different names. So like we called it the infinite bus before. You also hear the word slack bus used to refer to that. So infinite bus, slack bus, reference bus, whatever it is that we want to call it, it's that for which the voltage magnitude and the angle are known. And we normally don't have to solve for anything for that bus. Okay, bus number 2, or the second type, voltage controlled bus, PV bus, generator bus. Again, you'll hear all those terms used. For that type of bus, the the scheduled power injection, real power injection is known, and the voltage magnitude is known. Normally what we're going to be solving for is the angle, the voltage angle. We have the load bus, also known as the PQ bus, and for that one, the scheduled real and reactive power injections are known. We don't know the voltage magnitude or the voltage angle. Depending on what type of method you use, it can be easier to solve systems with more PV buses because the number of unknowns is fewer. Okay? It doesn't work that way for all different methods because in some of the methods they link the magnitude and the angles together, so you're kind of stuck solving for both regardless of whether you want to or not. But for some of the methods, we'll pull them out separately. So it'll allow you to eliminate equations. Like whatever expression is used to update the voltage magnitude for the PV buses, we'll just cross those out because we don't need them. So the number of unknowns in the system will be equal to the number of PV buses plus 2 times the number of PQ buses, right? Because we have 1 unknown for each PV bus. We have 2 unknowns for each PQ bus. So if you look at that 3-bus system that we had in the very beginning, which had 1 infinite bus, 1 PV bus, 1 PQ bus, how many unknowns do we have for that system? We have 3, right? We need to figure out what the voltage angle is at the PV bus, bus number 2, and we have to figure out what the magnitude and the angles are for bus number 3. Why is the slack bus absolutely necessary for a load flow analysis? I've talked about this already. It's an over-constrained problem if you don't have the slack bus or the infinite bus in there. And to go into a little bit more detail, you end up with a circular problem if you don't use a slack bus. Because you can't balance the generation and the load without knowing the loss. You can't define the losses without essentially solving for the system state. And you can't solve the system state without knowing the generation and the load. Okay, so it's a chicken and egg type of problem. Now, there are ways to get around that. Essentially, if you solve the entire